So I'm going to review this tweezer today. This has been sent to me at no cost by Zotek for the purpose of review. That's exactly what we're going to do. Now, the first thing I'm going to point out is the packaging. Now, you think, packaging's a bit boring. Well, yeah, it is probably a bit boring. But from a marketing perspective, I can see a bit of a issue here. Can you see what it is? Now, if you have OCD, this is going to be screaming at you. Yeah, just like that. Thanks, cat. Text is up this way. LCR text is up the other way. Which way should you hold it up? I think Zotek needs to flip this text to be on this side of the imagery on both sides of the box. Just a minor thing, but this is really screwing my OCD. Right, so you got this little case inside it. Carry/storage case. Get a little manual with specs and stuff on it. A USB-C charging cable. I think you might be able to do firmware updates through that as well. I'm not certain, I could be wrong, but I imagine you can. And here is the actual unit. Pretty small, 3 buttons on the top. Now we've got this little film we have to peel off. We have to do this properly though. Now over the tradition of peeling these films off, you have to use tweezers. Oh yeah. Okay, that's the silliness out of the way. Let's turn this thing on. Push that button on the top. Screen turns on. Nice bright screen. Now don't forget, my lighting here is actually really bright because I'm obviously doing videos. So I've got quite bright lighting here. And this is still easily visible. It's actually even easier for me to see it than you can see on camera. Right? It's actually is standing out really well. That's a good start. So we've got auto mode in right now. It shows us 0.6 volts, 1K to 1 kHz. Yeah. Series resistance 54 mega ohm, dissipation 34, 67. Anyway, because it's obviously just free floating in air. So let's look at the menu system first, and we'll look at actually doing some testing and stuff on it. So hold and level, frequency and menu, and obviously the mode and power off. If I hold it down, is that power off? Yep. Okay. Turn it back on again. All right. So obviously this is the ZT-MD1. To be clear about this. So let's look at the whole thing first. So you do a hold on that, just push it. Yep. Hold that. Here we go. Hold measurement. Okay, so that works fine. So the next thing we got here is level. So let's hold. If you just tap it, hold it down. That changes levels. So you've got 0.3 volts, 0.6 volts. Switch tone between those two. Okay, it's not particularly high levels. Half a volt. Don't know. Maybe I can do LEDs. I don't know. Actually. Leave on 0.6, yes. So look at frequency and menu. Push this. Push that, changes frequency. So that's 10k, it's 100 Hz, 1k, 10k. So those are the test frequencies. And it's hold it down. Goes into the menu. So you've got different languages, direction left and right. So you can flip the screen over. So if you're left-handed, you can flip it to the left-hand side. So you use it in your left hand. Volume 100% because there's a little beeper in there. Backlight is currently set 80%. I always recommend when backlights, turn them down, have them as dim as you can see them. It does two things. Firstly, in little handheld devices like this, it helps put on the battery life. Secondly, it helps put on the backlight itself. A lot of LEDs don't like being driven hard for long periods of time, and if you've got something which has got a backlight on it, and it's LED backlit, or anything really, you drive any of them hard, it shortens the lifetime. If you drop it down even 10%, it might double the lifetime of the backlight. I mean, I'm speculating here, but my experiences, I always turn them down. TVs are renowned for it. You get a TV, brand new, its backlight's 100%, and they'll burn out in a few years. Drop it down to 90%. Drop it to 8% if you can, and you'll find that TV will last a lot longer before it dies. So that's that one. So timer, 15 minutes, which is obviously like an auto power off time. Calibration. So you can do some calibration thing on this. I don't have to read the manual for it, but you can calibrate it. Restore, so factory defaults, and about, which is version 1.4. And that's that. Hold it down, get back out. Yep. And then we've got modes. Let's push tap it for mode. So resistance mode, capacitance mode, inductance, diode, beeper, contingency test, That's pretty quick. And back to auto mode again. Okay. Well, I suppose you should actually have a look at the manual before we actually use the thing. I'm not going to read it. You can read it. There you go. Do some screen grabs or something. I don't know. Specs there. Handy things to know. Reference. Hope you can see those okay. They vary depending on frequency and resistance and capacitance and inductance, so the actual accuracy does vary quite a bit across the range. Worst case is 5%, best case looks like it's about 0.5%, depending on frequency and value. General specs there as well. Auto power off, interestingly, says 5 minutes 120. Does that mean it's 5 minutes to 120? I think it must be. And calibration setting 0 to 10 megohm and an open. Maybe it's got multiple calibration points. And there's the back. Information about the buttons, operation stuff. Tells you how to do calibration there as well. Calibration includes 0, 1 ohm, 10 ohm, 100 ohm, 1k, 10k, 100k, 1 meg, 10 meg. I can do, I think, all of those if I really want to. I do actually have a whole bunch of standard resistors as well as a resistance calibrator, and I can do these calibrations if I need to. Inductance stuff as well. Just general information. Okay. Let's do some testing. I've got my D5000 just here. It's a fairly well trusted LCR meter. Good accuracy, that sort of stuff. So these are quite well known meters and they're very popular. There's a lot of these out there. Now I've also got this other tweezer here, which is the Shannon tweezer. This is the ST42. These are also available online. I thought it'd be a good comparison for a tweezer. You know, tweezers testers always good. This does LCR as well, so it's very much equivalent to this thing. I think these are more expensive though, and this also has a little calibration board with it, which gives some reference capacitors and things like that, so we can test both tweezers on this board and see comparative results between those. These tweezers are very accurate. I know these ones can be trusted because these basically agree with what the DER says. I'll be comparing this with the DER, so it should be really comparable. You see here I've got a container full of capacitors. These are ones which I've pulled out of equipment. Some are good, some are bad, some are really bad. I've got a small selection just here. I've also got some inductors. You know, people look at LCR meters and always think of capacitors, testing capacitors, because that's the thing you use them most for, is testing capacitors. But, you know, you have to remember, it's an LC and R. It does inductors and resistors too. Now, that little board I've got on here has got some resistors on it, so we'll look at those ones. Of course, I could get a item out and just check some standard resistors and stuff like that. I do actually have some standard resistors. I do actually have some precision resistors I could use, which I could use on this. But I think this would be good enough. Let's look at capacitors first, because this is going to be the most likely thing you're going to use an LCR meter for, is checking capacitors. I know some of these capacitors, I think all of these capacitors are basically bad to varying degrees. And I do have some ones which are probably okay. I think this one here is probably okay. We could check that one. Let's test some capacitors and I'll check it against the DER as well. This is in auto mode. I might change it to manual mode because I'll change frequencies to match what this is. Right, so this is at 1k right now, and so is this in auto mode. So let's just go for this small cap first. We'll go for the smallest ones upwards, alright? Small cap. So ESR 3.9, 6.4 microfarad, dissipation 0.15. Okay, so we're getting on this one at 1 kilohertz. Let's test it on the DER. It's in auto mode at 1 kilohertz, so it should be similar. 6.5 microfarad, 1.5 dissipation, which is what we get before. Now I have to go to manual mode on this thing in order to get the readings I want, because I want to go to ESR. 3.77. Very, very similar readings. It was getting, oh, there you go, 3.8 now. 3.9. It's basically agreeing at 1 kilohertz. Same frequency, it's agreeing. Now actually what we could do is go to a higher frequency. Let's do 10 kilohertz, because this does 10 kilohertz as well. Let's try that too. Do the same again. So again, 2.3 ohms, 5.8 microfarad. And then go down to 100 hertz, which this also does, 17 ohms and 7.4 microfarad. Now, when I'm doing capacitor testing, I almost always use 100 hertz or 120 hertz, depending on what's available to me at the time. 100 hertz is like my go-to. Reason being, this number has got much more variation between a good capacitor and a bad capacitor, right? So you can see here that we've got 18 ohms. But if I go down to 10 kilohertz, we've only got 2.5 ohms. So the difference between a good capacitor and a bad capacitor is only a couple of ohms. It's much harder to see. So which is why I tend to use 100 hertz, because it's much more obvious between a good and a bad one. Okay, just thought I'd explain that difference. Why I use 100 Hz a lot of the times, because it's more obvious. We've done 100 Hz on that. Let's just do 100 Hz on this one. Frequency is this one. So 10 kHz first. 5.8 microfarad, 2.2. So it's basically the same. Same readings DER is giving. Let's do 100 Hz. 7.5 microfarad, 16 ohms. Very slightly lower resistance there, but not much in it. Okay, it's still much more obvious. Let's try another capacitor. Let's do the next size up. Yeah, 205 microfarad, 3.6 ohms, 100 Hz. Do the same on this one. $206, 3.2 ohms. Very similar. Right, so it's tracking with the DER. Well, that's quite an important thing. You want your meter to be reliable and trustworthy, which is why you need to make sure that you can actually do these things. So let's do this capacitor here, 33, and that's measuring 9.3 ohms, 9.1 maybe. It's drifting down slightly. It's probably because it's charging the capacitor up. See that? Okay. Call it 34 and 8.6. We'll call it that. Okay. What does this think of it? 34, 8.4. Not bad. Next largest cap. 440 microfarad. 371 milliohms. That's not bad. That's down there where it kind of should be. 370 milliohms or so. It's dripping very slowly. Maybe it's a bit of capacitor self-heating going on, possibly, or maybe it's a voltage thing. Yeah, 360 milliohms, 441 microfarad. So this capacitor is probably okay, or close to okay. 440.3 ohms. Now, if you change frequencies, you can get different scaling on this thing. So I've gone to 1 kHz now, but you've got an extra digit of resolution. 10 kHz, can't measure it, it's too big a capacitance. Another reason why I like to use 100 Hz, because it's better suited to these kinds of capacitors. Okay, next one. I can just about get onto it. There you go, 11 microfarad, 2.2 ohms. I know it's not particularly exciting, but it's proving that, hey, it is matching, right? 11, 2.3. Still continues to match. I think we're seeing a good correlation here between these capacitors. What it's doing is matching. 140 at 1 ohm. $140.9 ohms. I think I've proven the point. Now this one here is an interesting capacitor. You'll see why in a second. It's not registering as a capacitor. See that big M, 80 meg ohms or so, not measuring at all. Stick it on the DER. What does that think of it? 195 meg ohm, 4 picofarad. Yeah, it's like, this is not a capacitor. This capacitor is completely dead, which is a good one to check on. Now let's just, for argument's sake, let's quickly look at the Shannon Tweezer version, and we'll look at a couple of these just quickly. 7.4 and 16 ohms. That sounds very familiar, doesn't it? That's exactly the same as that thing was giving. Next one, 203, 3.6 ohms. 204, yeah, basically the same. Next one, 33, 9.5. Again, very similar. 437, so that's slightly lower there. Resistance is 300 milliohms. Again, basically matches. So they're basically all within a really small margin of each other, which is good. That's exactly what you want. So that's capacitors done to death. Let's look at something else. So let's grab a inductor. This is a 1 microhenry. I'm doing 100 Hz on a DER. It's measuring as 5 microhenry because of frequency, because don't forget inductors are very frequency dependent. Well, capacitors are slightly too, but in the opposite direction. Like in the capacitors do too high frequency, you'll lose ability to measure the capacitance. Inductors do the opposite. You go too low frequency, you won't be able to measure the inductance. We have to increase the frequency in this case. Let's do 1 kHz. 1.2 microhenries. Okay, we go 1 kilohertz, see how that goes. That's 1.2. We have a Q of 0.17. I don't know if this does Q actually, we'll find out what it does on screen with the inductor. Haven't tried inductors yet. And there we go, getting 0.9. We have a Q of 0.09. This is really small inductance, so it's not surprising it's a bit marginal with that one. Let's go to a 3.3. Again, 3.2. A Q of 0.2. Oh, hold on, I think I'm squashing the wires together. I'm squeezing too hard. Alright, so 3.2 with a Q of 0.22. That's what the DR says. Q of 0.28. So they're really close. Let's get a 10 microhenry. I might have to change frequencies as well, we'll see how we go. 10 is doing 9.9, Q of 0.1. I've got to try and hold this one at the same time, so it might affect the readings. There you go, 9 and a Q of 0.09. So the Qs are very different, interestingly. This one here is a 470. I might have to increase the frequency again, because I'm touching it, it might be affecting things. Yeah, 460, Q of 0.52. Let's change frequency. It's doing 10k now. 425, Q of 3.8. Alright, very different. I think the 1 kilohertz is suiting it better. 454.5. Let's do 10 kilohertz as well. 421, 3.8. Very similar. So these are definitely correlating with each other. So that's good. Inductance seems to correlate. Capacitance correlates. Let's check some resistors. So this test board is actually from the Shannon tweezer. Comes with it for doing calibration and verification stuff like that. So I'm going to use it for this tweezer because, you know, why not? This is a 10 ohm resistor. Stick that in there. 10.01. Perfect. This is 100. 9.97. This is 1k. Yep, that's fine. 10k. Yep. 100k. Yep, very close. And 1 meg. Very close again. We also have a diode and some other capacitors and stuff on here as well. So let's look at diodes. This is still in auto mode, so we can pick a diode with auto mode, shall we? Might go specifically diode mode, that's right. No, not looking at that, so let's do modes. Let's go diode. And see what it thinks. Now don't forget, it's only got a 0.6 volt level there, right? That may be problematic on some diodes. I think it means you can't test LEDs with it, for example. We can verify that. So there we go, that says 0.5 volts drop. And it also tells you the polarity. Just here, see that? So if I reverse it, polarity is now shown the other way. The diode symbol, so it tells you which way the diode actually is as well. And here's another one. That is not, I think that's a green LED, is it? I think it's a green LED. Not sure, but that's not showing up at all. So that diode won't show up. Let's just look at the Shannon tweezer. Diode mode, same deal, right? And the other diode is measuring 0.49, so it actually correlates. So both are given the same forward voltage. Let's actually go to diode mode on the fluke here, and we'll see what the fluke thinks of it. Nothing that way around. And that way around it lights up 2.5 volts. So that's actually a blue LED. These can't produce enough voltage to light the LED up. So I actually think this is not a bad little unit. It seems to work pretty well. The battery's still looking really good. So obviously it's USB-C. So I think it is USB upgradable for firmware. And the battery's lasting quite well. I've been playing with it a little bit. I've charged it up once and I've used it probably 20 minutes or so, all up, I'm guessing. Maybe half an hour. Battery's still good, so that's excellent. It does a pretty good job. So another thing to consider as well is the tweezer type. Like this is Shannon tweezers. This weighs less than this. You can see there's obviously a bit of difference there in size and what have you. This is lighter. This is a bit bulkier. The actual tweezers themselves, I'll show you that in comparison. So this is Shannon tweezer and there's the Zoyi, and you can see there's a massive difference there. These are much finer tips on these, and these are obviously all 4-wire as well because of they need to be. up to the point that they get to the tips anyway. Alright, for the accuracy of milliohms. But you can also see when these come together, it just, I don't know, I'll squeeze them in my place, maybe better. They come together okay, that's fine. Slightly different profiles, which you prefer, I don't know, it's up to you I suppose. But this is just finer tips on these ones. But I think these would be adequate anyway. Let's actually get some SMD parts on a circuit board. Let's have a quick look and actually try testing some parts in circuit and see what happens. So here's a board which I've been asked to look at trying to fix. I may not be able to fix this one, but there's a few more like it which are very similar. And it's got various surface mount parts in it. I've got no idea what values these are. But we'll have a poke around with this and see what we get, and to see how it behaves. So make sure we're in auto mode, we are. And there's some parts down here, I've got no idea what they are. There's a stick on it. That's shown as a 6.6k resistor. That does say R1, so it probably is. There's a capacitor here, 135 nanofarad capacitor apparently. Another capacitor here. These may be in parallel as possible. That's measuring resistance. There's probably a resistor across that as well. Yeah, so various parts here. There's a capacitor here, so look at this. I'm testing at 1 kHz, and that might be sufficient for in-circuit. In-circuit testing can be problematic. 50 ohms across that capacitor. Let's go to a higher frequency. High frequency can be helpful in circuit, but if you're trying to measure things like electrolytics, like these, you probably won't get a measurement out of them. Let's try this one. Now I've got high frequency. Nope, still measuring as resistor. Let's go low frequency, 100 Hz. Now we're getting capacitance. There we go. Getting 800 odd microfarad. Because it's in circuit, you don't quite know what you're getting. You know, if you've got something which is clearly standalone by itself, it's a bit easier to test, but in-circuit testing can be quite hard. There's some more capacitors to see here. Let's see what these do. There you go, 100 microfarad. That makes sense. We've got these PTCs. Let's measure across those. That should come up as a resistor. There we go, 126 milliohms. That sounds about right. Low resistance, you would expect that. So we've got some inductance in here too. Let's check these inductors, shall we? Let's go inductance mode. Let's try and measure one of these. It's got 1R5 marked across it. See if we can measure that. Might be wrong frequency. Let's try changing to 10 kHz. I'm not even sure I'm getting onto the actual inductor side actually. I can't quite see how I'm actually getting onto the connections. Not sure I'm getting onto those connections. Let's have a look. I'm not really getting onto those. Let's check this one, see if I can get onto that one. No, those inductor styles aren't being very helpful. There's an inductor in parallel with this resistor. Let's measure across this resistor. There we go, 2.1 microhenry showing up there. And it's marked as 2.2. So it is actually able to measure that one, so it can do that in circuit. Just trying to get onto the actual connections is being a problem. In circuit of inductors is hard because it's a case of just trying to get onto the connections themselves. Actually, I haven't looked at continuity yet, have we? Let's do that one. Because right here we've got a fuse. So here we've got a fuse. And it also gives you a resistance reading at the same time. It is beeping. We've got these big capacitors in circuit as well. Let's just have a look at these. Change frequencies, 100 Hz. Let's measure one of these. See what we get. 857 for that one. And this one here. 852. And the 820s. So it can measure those in circuit. That's a good thing. So I've got these capacitors here. We should check these ones out. I've got it set auto mode again. Back to 100 Hz. Let's see if we can measure these. We'll get the probes on. So we're getting 105 there, because these two capacitors here are in parallel with each other. I think the biggest issue in circuit is trying to test these larger components, because you see what the probes are doing. You see how they're shaped. They tend to like the boat outwards, and as you bring them together, now put it with the background like that, right? You bring them together, then they kind of come right, but as you come outwards, they kind of bow outwards. If you're trying to test a component it's not necessarily the right shape. They kind of need to be bowed inwards a bit, and that's like the issue on trying to like measure these inductors and stuff. I can't actually get around the inductor because of the shape. It means they're actually hitting on the sides rather than at the terminals. So the shape of these, see, it's hitting on the top, not at the bottom, which means it's really hard to try and get onto the circuit board. So I think these actually need to be bent in a bit, actually, so they don't kind of bear outwards. I mean, if you look down them, they look like they go outwards. They do seem like they go out. They should be going in, which is what the other tweezers do. I think out circuit testing is better. In circuit's a bit tricky. Doing these tests with a multimeter or an LCR meter with probes would be better. So I just bent these tips inwards slightly using my trusty Leatherman. And let's see if we can get any different results with this now with connections on these inductors, because I really like to be able to test these in circuit. We'll go to inductance range, or inductance mode. Let's try another one which we couldn't measure before. Let's try this one. 1.3, 1.8. Jump around a little bit there. It says 1.5. So yeah, it says 1.5. And next we've got 3.3. Let's try that one. 3.7, 3.9, 3.5. That's at 100 Hz. Let's try 1 kHz. But bending those tweezer tips has definitely helped. Yeah, 1 kHz is jumping everywhere as well. It's probably activating circuitry. I think they should come like this, not straight. That's better. And probably slightly sharper. They probably need a bit of filing to get so it's got a nice tip, sharp point on the inside edge. Right now, because I've bent them, they're actually slightly wonky. So I won't be going flush to the board, it's just slightly raised. So a bit of filing will fix that. Really, it should come in the right profile to be able to do in-circuit testing, I think. That's kind of what they're meant for. So I've got it hooked up to the Keysight scope here, and I'm currently doing 100 Hz, 0.6 volts, and on screen here we're seeing 1.8 volts peak to peak, 100 Hz, RMS DC, 600 millivolts. It's actually doing really well. It's actually exactly what it's supposed to be. So let's do 1 kHz, check the same things again, 1 kHz, 0.6 volts, 10 kHz, 10 kHz, 0.57 volts, a drop very slightly there. Let's change the voltage down to 0.3 volts. We're getting 288 now. Back to 100 Hz. We're getting 303 millivolts. 1 kHz, 304 millivolts. So those are working just fine. But that's basically the waveform we're getting out of it. So it doesn't seem to matter which mode we're in. That's resistance. Go slightly closer. Capacitance. Inductance. Diode. Continuity. Auto mode. Let's go through them all. That waveform doesn't change at all. So what you're seeing on the actual output doesn't change to what mode you're in, which is interesting. So I'll just set this up now to test the capacitor. This is a 47 microfarad capacitor, brand new one. Got 0.6 volts, 100 Hz. We see 100 Hz on screen here, but we can see that the actual voltage has dropped a bit. It's now down to 200 millivolts. Now what I want to demonstrate to you is the fact that it doesn't change that much, but the voltage has dropped a bit. And if I change frequencies, watch what happens to the waveform. It's 1 kHz, and it's still reading something. 10 kHz, just about disappears. The frequency is too high for the capacitor. The amplitude of the waveform will drop significantly, and it won't be able to read it. I think that's what's going on there. That's 100 Hz. Let's get a smaller capacitor. So here I've got a 0.47 microfarad capacitor, and you can see we're getting 495 nanofarad, which is about right. Okay, it's 100 Hz, and then go to 1 kHz. Waveform didn't drop quite as much, so it's just touching on there. I've got to make sure I get it connection well. Yeah, it's measuring for slightly better there, 476. I do 10 kHz. Now we're getting 424, and there's still a waveform there, so it's still actually able to see something because the capacitance is having a much lesser effect on the waveform. Summary: it's a good little tweezer. I think the price is quite good on these too. Don't forget to check out the links down below to these, because there are links down below in the description to go to these things from the manufacturer. Just have a look in the description, it'll be down there. I think it's actually a good little tweezer. It's certainly got a tool, it's got a place. Now this has got a place. If you're doing out of circuit testing, this is a brilliant thing to have for that. In circuit, this is a bit trickier to use. I mean, it's not too bad. I mean, you can get on the components tree and stuff okay. Now I've been those tips, it's actually getting on a lot better. That would be reading better. That's getting on a lot easier now. So that slight adjustment to the tip angle makes a world of difference to it. They're certainly good enough to use, especially out of circuit. If you've got components not in circuit, it'd be perfect for that. But usually using tweezers because they're in circuit. I mean, you could have some surface mount parts on your desk and you're trying to measure them that way too. That's certainly possible, and it's perfectly good for that. As you saw, in circuit is possible, but potentially tricky depending on what you're trying to measure. As it is from all in circuit testings, not just these which have that issue. All devices have issues reading in circuit to some degree. Depends on the circuitry around the parts you're trying to measure. Some are easy, some are hard. For the price, you should always have yourself a little pair of tweezer units, and these being LCRs. The diode test I think is a bit limited. I think that voltage could really be higher. Only get up to 0.6 volts I think is a bit of a limitation. I think Zoyi should really look at increasing that to say 2.5, 3 volts, something like that. Say 3 volts, so you can light up LEDs and test LEDs, because that's certainly a useful thing to do. If you've got surface mount LEDs, I can tell you on screen which way around they are. So I think if they could modify this to go up to sort of 3 volts for LED test, they'd be much more useful. The current test is a bit low, doesn't really do it. It's a shame. That's like a missed opportunity there. Diode tests are usually something you want to have a reasonable voltage on, so you can actually test all diodes, not just some of them. Menu stuff is good. Display is really clear, nice and big and bright display. In that regard, the display on this is actually better than the Shannon tweezer, but the Shannon tweezer's got obviously a smaller body, so they've crammed a lot onto that small display. So yeah, I don't know, it's got pros and cons. I think if you are doing surface mount work, you want one of these sorts of things. You want something of this type, and this is relatively inexpensive, so I suggest maybe getting this one. If you want something which is potentially better for in circuit, better probes, that sort of stuff, maybe you want a Shannon tweezer. It really depends on your main usage and how much you want to spend. I know the Shannon tweezers get firmware updates because they listen to user feedback. Check out other links down below for other stuff, other reviews, repairs, that sort of stuff. Maybe you'll see me doing a video fixing this thing, who knows. Subscribe over there if you're not already subscribed, and there's a Patreon support link over there if you want to support the channel. Donate a couple of dollars a month to help me to buy things in mailbag or buy a bit of test equipment to do repairs on and do videos about. Catch you later.